Okay, so ladies and gentlemen, good evening. After this break of Ramadan, we will today start with a new talk from Dr. Abdellatif Bouaichi. Abdellatif Bouaichi, he's a Moroccan citizen, and he holds his engineering degree in 2014, followed by a doctorate degree in electrical engineering. And he worked very much on renewable energy. So all his work was done on photovoltaics, mostly. He did this in connection to the University Moulay Ismail, Morocco. Now he is professor in the Ecole Marocaine des Sciences de l'Ingénieur in Rabat. That's EMSI, Rabat. He conducted research and development for his PhD and I guess before in Erizen, Institute for Solar Energy, and Green Park. So this is in Belgrade. So he worked in very good conditions with a lot of facilities. And he will share with us today his talk entitled Field Performance and Durability of Photovoltaic Power Plant. By the way, he teach also in just recently in Paris, Est Créteil, where he was invited as research professor. So the floor is yours, Dr. Abdellatif.
So, Bismillah ar-Rahman ar-Rahim. Hello, everyone. Thank you very much, there, Professor Ahmed Inawi. So, firstly, I would like to thank all the members of the Virtual Learning University for their efforts to organize such webinars in such interesting field of research about renewable energy and especially photovoltaic. So today I'm going to give a lecture about a very interesting point, which is the performance and durability of PV plants in different climatic conditions. So as you know, among the various renewable energy sources, photovoltaic represents a good alternative for energy transition. So this technology uses the sun, of course, which is considered as one of the most abundant source in the world. This technology, of course, which is photovoltaic, needs to prove its reliability, especially in climatic condition with highest resource of solar energy, especially in hot climatic condition like desert condition. If we talk about the photovoltaic system, the most important component in the PV system is the PV module, which have to operate at least 25 years old with a specific degradation rate, means yearly power losses was about 0.8% per year. So if we need to improve the reliability of PV module, we have, of course, to understand firstly the so-called performance and durability. If we want to understand durability of PV module, we have to deploy a lot of PV technology in real climatic conditions, so to understand especially the different behaviors of PV module compared to each climatic conditions. So in this talk, I'm going to talk especially about degradation of PV module, performance of PV module, and the specific techniques used to specify the failures in a PV module. So my talk will be based especially on two case studies. So the first one is a study conducted in the climatic conditions of Morocco in the city of Rashidia. Rashidia is an arid climatic conditions. We conducted a comparison of 3 PV plants to investigate and to compare the performance of its technology, named monocrystalline, polycrystalline, and amorphous silicon. The second case study is the in situ inspection and characterization of the early failures of PV module, which were conducted in the climatic conditions of Ben Guerir in the Green Energy Park. As you know, the Green Energy Park is a platform for testing PV technology and CSPT technology. So in this talk, I would like to provide especially 2 cases for field performance and durability. The first one is the performance indicator to analyze the PV system. And the second one is the different measurement methods used in the market, in the research institute, to provide and to identify the failures in a PV systems. So let's start with the first case studies. These case studies have been, as said, conducted in Rashidia in 3 PV system installed at the University Moulay Ismail, the Faculty of Science and Techniques in Rashidia. So the title of this case study is In situ performance and degradation of 3 different photovoltaic technology installed in an arid climate of Morocco. So in this first case study, we will provide especially the performance indicator developed by the IEC Commission and the International Energy Agency in the task 13, which make a part of the photovoltaic power system program. In this part, we will discuss the most used indicator to evaluate the performance of PV system, independent on capacity, also independent on installed capacity, location, etc. So the second point that we will discuss is a comparison of the performance of this installed technology with other ones in different climatic conditions. And finally, we will evaluate the levelized cost of electricity for HPV system, finally to bring the most or to bring the highest reliable systems and technology for this region. So based on the International Energy Agency, and especially based on photovoltaic power system program, the main indicator developed to evaluate the performance of the PV system are especially the so-called performance ratio, final yield, and reference yield. So let's talk about these 3 indicators. Let's start firstly by the reference yield. If we want to talk about photovoltaic, we need, of course, especially to start by solar resources, especially radiation or insolation. The first indicator related especially to solar and to resources deployed in the region. The so-called reference yield provide especially the numbers of hours at standard test conditions, means 1000 watts per square meter. If we say that the reference yield equal, for example, 5, that means 5 hours, for example, per day. That means that every day we will have 5 hours of irradiation at 1000 watts per square meter. This is the so-called reference yield. If we want to develop and to monitor the reference yield in a specific region, we can deploy the pyranometer, so to measure the in-plane solar irradiation, or the reference cell also to measure the same parameters. So the second one in the indicator is the so-called phenol yield. The phenol yield is the output energy for a specific period divided by the rated power for the PV system investigated. So in this definition, we can define the phenol yield as the AC energy output for a particular period divided by the DC power of the PV array. So in comparison with the first indicator, this indicator provides especially information and data about produced energy for the specific PV systems. So if we look at this formula, we can say and that formula is such a normalized formula to compare especially different PV system with different capacity. With the phenol yield, we can of course compare, if you want, a PV system with 2 kilowatt installed capacity with other one with, for example, 100 kilowatts as installed capacity, because the reference yield provide a value with the unit of kilowatt hour per kilowatt peak. Means that each kilowatt peak will produce a special, for example, specific energy in a specific period. So we can, of course, calculate the phenol yield for example, daily phenol yield, monthly phenol yield, or yearly phenol yield. So let's take a summary or about the first indicator. The first indicator provide information about insolation, and the second one provide information about electrical parameters. So based on the first one, the reference yield and the phenol yield, we can get the so-called performance ratio. What does performance ratio mean? The performance ratio is a measure of the efficiency of the entire plant as a converter of solar irradiation to AC energy. It can be considered, for example, as a measure of yield for normalized sales, for different sales, for different available solar irradiation. With this parameter, with the performance ratio, we can compare PV systems with different capacity and installed in different sites. So with the reference yield, we cannot compare, for example, a PV system in Morocco with other one in France. So we can compare, if you want, two PV systems installed in the same region with different capacity. However, the performance ratio, with the performance ratio, we can compare different PV systems independent of their capacity, also of their installation site. So we can also talk about the so-called performance ratio corrected. If we want to take into consideration the effect of temperature on the PV, on the performance ratio calculation, we can get this formula. This formula is the calculated performance ratio divided by 1 plus this parameter. This parameter is the temperature effect on power multiplied by temperature of the module minus the temperature, the reference temperature. The reference temperature is 25 degrees Celsius, especially the temperature of the cell. So as a result, for the 3 PV system installed in Rashidia, Morocco, we get especially this result. This result is the evolution of the performance ratio for the first technology, the second technology, and the third technology. It's about about 3 years of monitoring, about 36 months. So we can get an idea about the evolution of the performance So this is January, and this is during June, July, etc. So we can find that during winter, the performance ratio is relatively higher than during the summer, because this is relative to the effect, the temperature effect on the performance ratio. However, during, for example, autumn or during spring, we can find highest value of performance, because during spring we have a high soil radiation and we have lower temperature. So this is for the second systems. We have also the same chip if we compared the two chips together, and it's also the same one for the third technology. So if we want to get the average value for the three systems, so this is for the first one, this is for the second one, and this is for the third one. This value are listed with other one worldwide. For example, this is for Russia. The average value is about 82.5%. For monocrystalline technology is about 82.2, and for the second system is about 81.6. So if we compare the three technology, we can say that the performance of polycrystalline silicon is higher than monocrystalline and amorphous silicon. If we need, for example, to take an overall idea about the value of the performance ratio, we can say that that a value of a performance ratio higher than 70% is good. This value of 80%, 82%, 82%, 81% means that the performance of the PV system investigated in the region is especially higher and with high performance. We can look at the other systems. Here, for example, in the South Africa, the value is about 84%. The value, for example, for Spain, they provide a value of about 49%. Yeah, this can be, of course, related to the climatic conditions, and it can be related to a specific, for example, orientation and localization of the PV module. If the PV module is not well localized, we can get some error in the calculation. So based on this performance, on this capacity, we can remove and we can go to the economic evaluation through the evaluation of the levelized cost of energy. As you know, of course, the levelized cost of energy can be evaluated through this formula and through other formula deployed in several papers in the literature. So this formula of the LCOE take into consideration the initial investment of the project, the operation and maintenance costs of the project, the performance degradation rate for the PV module, the produced energy during the first year, and the discount rates of the money for the specific site of investigation. So based on this formula, we get the value for the three system, and we get that the meanest and the highest economical PV system is the one with lowest value of the LCOE, which is polycrystalline silicon. So as a summary, if we want to investigate the performance of a PV system, we can refer especially for the reference yield, for the final yield, and for the performance ratio, and finally we can calculate the levelized cost of energy. If you want, for example, to provide value of the reference yield, you can measure it with especially reference cells or with pyranometer. And there is also some websites, for example, PVGIS, which can provide you some approximated value of the reference yield of your region. Let's go to the second case study. In the second case study, we will move especially to the degradation analysis of a PV systems, especially to talk about failures, to talk about degradation rate, to talk about PV module, and to talk about climatic condition of specific site of investigation. In this case study, we will especially describe the basic and the most used method to identify failure. So this is an important tools for PhD, for masters, for students to take an idea about the measurement and the methods used to specify and to describe PV failure in PV systems. So we can also report the main PV model degradation mechanisms for each methods. For the methods, we will talk about 4 methods used especially to identify different PV degradation in the field. We will also talk about specific degradation mechanisms in the climatic condition of Morocco. So especially in the green energy park. Let's start. So this case study have been conducted in the climatic condition of Benguerir, and especially in the platform Green Energy Park, which have been established in 2014 with reason and with the University Polytechnic Mohammed VI. So in this platform, there is a lot of PV technology deployed outdoor. This is a test facility with different technology. If we can take a look here, we have, of course, amorphous technology, crystalline technology. We have a part for the exposure of PV system. And in right side, we have exposure of PV module, so especially to take an idea about the behavior of PV module alone without the operation and without the effect of system. We have the difference mounted, fixed mounted, tracking, etc. So the deployed PV module in this test facility, there is a lot of technology, certified EIC 61215 for crystalline technology, and 61646 for amorphous technology. So in this PV platform, we have specified especially 4 PV systems. Here are the PV systems. The first one is a crystalline silicon technology. The second one is also monocrystalline. The third one is monocrystalline, and the fourth and fifth systems are polycrystalline. So this system have been deployed for more than 3 years. Why I have provide this information? Because there is a lot of recommendation to evaluate the performance and durability of the system. There is a recommendation by especially in-rail laboratory, by especially the recommendation of the task 13 of the PVPS. The PV module to be investigated should be deployed in real climatic condition at least 3 years. So if you want, for example, to calculate the degradation rate for a specific PV module in a specific region, we have to work on PV module worked in real climatic condition at least 3 years, 4 years, 5 years, so 3 years at least. So let's take a look about the the different layers of a PV module. The most important layer in the PV module is the PV cells mounted together in series or in parallel in the half technology. So the solar cells have to be protected against climatic conditions with 2 layers in the front side and 2 layers in the back side. In the front side, we have the encapsulant and the glass. And in the back side of the cells, we have the same encapsulant and the backsheet. So if we will take about PV module, we can talk about glass encapsulation and glass backsheet encapsulation. So in this picture, we have glass backsheet encapsulation. So this layer, which is of course the most used layer in the market actually, is the EVA, ethynyl vinyl acetate, have several rules in the PV module. It have especially 3 rules. The first one is to protect, to isolate PV cells electrically against the frame. The second rule is to protect PV cells against humidity. And the third rule is to make a soft layer of the PV cells to make these layers as soft as possible. Okay, because we will have in the operation condition we will have flexion of the PV cells, and as you know, the PV cells are very sensitive to like mechanical effect, and with the lowest effort and stress, we can break the cells. So the encapsulant will make as a soft layer of the PV cell. So the front side we have the glass, which will prevent like UV light, deposition of dust, etc. And the back side, of course, we can protect against, of course, the effect of temperature, the effect of humidity, etc. We have also the junction box in which we will find especially the bypass diode, the electrical terminal of the PV module. So if we talk about fillers in a PV module, that means that the filler will be found in a specific layer. For example, in the frame, in the glass, in the encapsulant, in the solar cells, in the backsheet, or in the junction box. To detect and to specify this filler, we have especially to understand the different methodology used in the market to specify the defects of the PV module. So here are the most used methods to specify the fillers in a PV module. Let's start with the first one. The first one is the most used one and the simple one, the visual inspection. The second one is the so-called electroluminescence imaging. The third one is the infrared imaging, and finally, the measurement of the electrical parameter. The 3 methods, visual, electroluminescence, and IR imaging, will provide qualitative information about defects. And the fourth one will provide quantitative information and details about degradation. Okay, so we will discuss each one alone, and we will also talk about the specific degradation mode provided by each methods. Let's start by the first one. The first one is the visual inspection. The visual inspection is the possibility to detect such anything normal in the PV module, especially in the different layer of the PV module, in the front side or in the back side. In the front side, if, for example, we will look at the front side of the PV module and we found there is a break in a PV cell, there is, for example, a problem in the frame, there is a corrosion of the, for example, of the finger interconnection. There is, for example, the different colors of the different layers. For example, the color of a PV cell, the color of especially the EVA, etc. Or problems in the backside, for example, in the junction box, in the electrical connection, in the frame, in the backside, etc. Let's talk about specific degradation failures detected in the field. So here, the first example of a specific degradation mode detected. The first one have been detected in the Green Energy Park test facilities. This is the so-called broken glass. This can be happen, of course, with some abnormal behavior of a person, or if it can be also happen with, for example, the effect of holes on the PV module. So this, of course, can affect the optical properties of the front side, and of course can affect the energy produced of the module. The second one is the so-called delumination. Delumination means there is a humidity penetration between the different layers of the PV module. Also, this problem can minimize and arise the wretched solar irradiation by the PV cell. So each part with delumination will have less power of solar, and therefore will provide less energy produced. This is a delumination for a crystalline module. This is a delumination in the fingers, also in the ribbons, and this is a delumination for a thin film PV module. Let's switch to another visual degradation. Okay, this is the so-called burn marks. Burn marks is like a localized heating in the front side or the back side of the PV module in the electrical interconnection of the PV between the PV cells. This is in the front side. We can observe that we have here a specific burn mark. This is the ribbon, and this is the fingers. So this is like the Joule effect in the PV ribbon. In this ribbon, we have a specific localized heating, which will provide and which will block the ribbon of the connection of the PV cell. This is in the backside. This problem can be visualized in the front or in the backside as seen in this picture. Yeah, this is a very famous visual modes of PV module, the so-called discoloration. What is discoloration? Discoloration is a change in a color or in the color of the layer. Okay, so the layer, especially the layer of the encapsulant, especially the encapsulant, the EVA, is the layer with a transparent color, with the effect of UV light, with the effect, of course, of temperature. The color of this layer can be changed. If this layer changed, there is also some optical losses in the PV module, and hence the PV module will produce less energy. Yes, we have also delamination of the backside. Delamination of the backside, or the so-called bubbles. Bubbles is like a specific delamination on the backside on the PV module. This delamination are, of course, the penetration of humidity in the backside of the PV module. Yeah, we can also talk about the so-called Snell trails. Snell trails is like the discoloration of the silver paths for the grid lines on the cells, is like a Snell trails. Yeah, we can look at this. Yeah, this is some oxygen reaction with the silver. This is a detected Snell trails in a PV module in the green energy park. This is other one in also for other system. So in a published paper for me, I demonstrated that these Snell trails can be used as indicator for the existence of cracks in the PV cells. So if we have found that there is Snell trails, that means that automatically in this part we have cracks. This cell are cracked in this part. Okay, let's talk about the junction box. In the junction box, we have, of course, the electrical terminal of the PV module, and we have also the bypass diode to protect PV cells and the PV module against partial shading. So here we can find that there is some heating of the junction box. There is also, of course, some corrosion of the junction box. Yeah. So let's switch actually to the second methods to detect failure in the PV module. What is the need to use thermal imaging or electroluminescence imaging or IV curve measurement? If we can discuss later that there is a lot of degradation detected by visual inspection. Why the need for thermal imaging? So sometimes there is some problems which cannot define and we cannot detected by visual inspection. So in this case, we have to use powerful techniques to detect some non-visual degradation. Here we have the thermal imaging. The thermal imaging is the distribution of temperature along the front side of the back side of the PV module. In a normal PV module, we have to find a homogeneous the temperature distribution on the PV cell. If we found that there is some difference in the PV cells temperature of the same PV module, that means that there is a problem. So this problem can be defined and detected by thermal imaging. So to use thermal imaging, we have to use IR camera based on the IEC 62446. So this is the recommendation and the certification to perform these techniques in outdoor conditions. So the most detected defect with thermal imaging is the so-called hotspot. What hotspot means? Hotspot means there is there is a difference in the temperature of the same module. As you know, in a PV module, we have a series connected cells. So in the same module, the same current will go through all the cells. If there is a difference in the current of each cell, we will have a specific inhomogeneous current in the specific cells. That can happen by, for example, partial shading, defects in a PV cell, bypass diode failure. We can also talk about drone-based infrared imaging. So we can inspect, for example, a PV plant. If we talk, for example, about large scale, we cannot inspect each PV module alone. We can talk about drone-based PV module because these techniques can be performed with the normal operation of the PV system. Okay, this is a video of the operation of drone-based PV detection. So with the drone, we can detect, for example, some hotspots. Can be detect seen her or her. Yeah. Okay. Okay. Let's go to the third specific methods. The third methods is the so-called electroluminescence imaging. A PV module can convert sunlight into electricity. EL imaging is the conversion of electricity into light. Yeah, we will polarize the PV module, and the PV cells will provide light. If there is some part or some inactive part of the PV module which will not provide light, that means that there is a problem in this part. This problem can be detected by electroluminescence imaging. In the electroluminescence imaging, we have to take the PV module in a dark environment, for example, in the indoor conditions. So this is a chamber of EL imaging deployed at the Green Energy Park that I have used for about 4 years of research. So we have to use the PV module and to connect the PV module with a power supply, and to connect also the power supply with a laptop, and we CCD camera to detect PV defects. So take a look about this camera. So this is a PV module with visual inspection. If we take a look about this PV module, we can bring that there is no defect in the PV module. However, the EL image of the same module provide that there is a lot of inactive area in this module. Her, and her. So that demonstrates clearly that visual inspection cannot describe all the defects in a PV module. So we have to use and to refer to powerful techniques to detect such problem in the PV module. So this is the EL images of cell with no defects. So this is normal cells. The first one, the second one. This is a monocrystal line. This is a multicrystal line. There is no defect, just for inhomogeneous distribution of color of the polycrystal line. This is for the homogeneous color of the monocrystal line. So, okay, this is the failure category in the EL image. So this one is plus or minus with non-defect. Of course, take it's okay, Professor Inawi?
It's okay.
Okay. So in the second one with the sun simulator, we have to take the PV module indoor in a sun simulator, when we can fix the value of irradiance and the value of temperature. Then we can automatically calculate the electrical parameters of the module in their standard test conditions. So I have conducted the IV curve measurements in real climatic condition and with sun simulator. This is my picture in Green Energy Park. I think this for 2016. 16 or 17. Okay, this is the IV curve. This is the IV curve. With this IV curve, we can of course get the maximum power point, the maximum voltage, and the maximum current. This shape in blue is the IV curve. This is the power voltage curve. Based on this curve, we can get, of course, the so-called degradation rate. So let's talk here about the local degradation detected in the climatic condition of Morocco. So the first one is the hotspot, which is driven by partial shading, soiling, and cell defect. We have also found delamination. We have found also snail trails, which is driven by cracks and the quality of the encapsulant. We have also PID. We have also micro crack, and we have also discoloration of the AVA. Okay. We have also calculated the degradation rate for different PV systems. So before to talk about the found value, let's talk about the provided value by the manufacturer for PV module. For the manufacturer of PV module, the manufacturer provide about 0.8% per year as degradation, as the power degradation for each PV system. However, in such climatic condition of desert climatic conditions, or also desert climatic conditions or harsh climatic condition, we have found that there is a high value of degradation rails, which reflect that the PV module are deployed actually in the market, are not very suitable for this specific climatic conditions, and we need to provide and outdoor characterization to provide solution to prevent like defects and improve the durability of the PV module in climatic condition of desert. Yeah, here is a proof that in desert conditions, this is a study published by the INRAIL laboratory, demonstrates that in desert conditions, the degradation rate can go about 4% per year. Yeah, it's very, very high. If we talk about 4% per year as a degradation, we can get 20% of degradation in about 5 years. Yeah, but the manufacturer proved that the PV module can operate for 25 years old with at least 80% of their initial power. Yeah. Okay. So as a result, we can, if we want to take a general look about the degradation rate, it can be, of course, managed by age of the operation of the PV module, the measurement uncertainties, because why? Because if we talk about degradation rates, we can find that in some studies, a lot of researchers use nameplates as a reference value, and other studies we found that they use especially the first measured power of the PV module, and this is the most and the recommended used method. It depends also on the technology, on the product type, monocrystalline, polycrystalline, amorphous, etc., and the mountain type. So if we want to provide, for example, mitigation solutions, the mitigation solutions should be provided especially to decrease the levelized cost of energy for the PV module through especially the reduction and the replacement of expensive materials. Let's talk about, for example, EVA. EVA can be replaced by, for example, the polyethylene or enomer. There is a lot of alternative in the market. Accelerating the manufacturing process. The process to produce a PV module with EVA take about 20 minutes for one module. So if we take about fast Turing EVA, we can talk about 10 minutes. And especially we can talk about 5 minutes to produce one model. So the performance should be increased through the using, for example, of tracking, of new technology like PERC technology, TopCon technology, etc. And also to the production related cost should be decreased. Okay, so here are some recommendation for the best practice guidelines for the monitoring of PV systems, provided especially by the last published report of the photovoltaic power system in the task number 13, published in 2022. So they recommended that the irradiance should be measured. So with especially in the plane of array of the module, they recommended also that the module temperature should be measured at the backside of the module. Yeah. They can recommend also to measure and to monitor the local meteorological data like wind speed, like ambient temperature, like for example wind direction, humidity, etc. They recommend also for to make alarms, for example, for loss of communication, plant shutdown, plant with low PR. For example, if we take the plant with low PR, why? If we found that there is a low PR, that means that there is a problem. Why? Because in the PR, we divided the produced energy by the solar resources. Is there is a lot of solar resources, automatically we have to produce high energy. Is there is less solar resources, automatically we will have low produced energy. So the average value of the PR is about 70%, 80% is a normal. If we found, for example, that there is 30%, 40%, there is a problem in the PV system. The infrared thermography should be also performed with a special condition, at least, for example, here as recommended 600 watts per square meter in the solar radiation. Thank you very much. Yeah, there is also electroluminescence inspection to take an idea about the different degradation modes. So in this talk, we have talk about a lot of points in the field performance and durability of PV power plants. Let's take a summary. A PV system composed of different parts: the PV module, the parts for conditioning the produced energy, and finally the grid or the load. So the PV module is the most important parameter in the or components in the PV systems. The PV module composed with different layers. If we want to inspect the PV module, we have to inspect the different problem detected in special layers. For example, the front side, the cells, or the back side. To inspect this degradation, there is a lot of methods deployed in the literature, in the market, etc. Each PV degradation methods can provide specific degradation modes. For example, with electroluminescence imaging, we can find cracks and micro cracks. With visual inspection, we cannot find micro cracks. With AL imaging, we can find PID. PID cannot be detected with visual inspection. And also, we have to perform the performance measurements of the PV plant as recommended by the PVPS program task 13, based on reference yield, final yield, and the performance ratio. All that, especially to reduce the levelized costs of energy for photovoltaic. And thank you for your attention.
Thank you, Dr. Abdellatif Bouaichi, for this very interesting and crystal clear talk, where you talked about all tools, all diagnostic, to have at the end of the day module which can work for more than 25 years. And regarding the performance ratio and the LCO. So we open your talk for discussion. Before we go to discussion, there is one questions in the chat. So one attendee, Mr. Azuzut, Ali Azuzut, he asked you, he thank you first for your talk, and he asked about the degradation performance D, he make D here, small d, in the LCAO constant or variable. Could you please elaborate on that? Do you understand the thing, what he want to say?
Yeah. So thank you very much for this interesting questions. So in the LCR-OI, we can take into consideration the degradation performance of the PV systems. If, as the question of Ala, the degradation rate can be fixed. If we can, for example, measure it for at least 3 years. If the degradation rates are, for example, measured for just 1 year, we cannot use it for the levelized cost of energy. If we calculate the degradation rate for example, 3 years, the average of 3 years, we can make this information. If you have, for example, the evolution of the degradation rate for your PV system, we can use this different value of the degradation rates. The same, for example, for the produced energy, for the operation and maintenance costs, we can use just for this for the first years, and we can make assumption for the next years. Unless we can use just one value. Okay.
Okay, thank you very much. So now we open for the discussion. I believe that Ustad Salem, he's here to open the micro for everyone who want to talk.
It's open.
Yes. So please, if you have any questions related to this topic of degradation, performance ratio, visual photoluminescence, infrared, IV characteristic, power output characteristic, please go ahead and ask. We have today an expert. By the way, this talk tell us that in Morocco we have expert in the PV systems, and also we have all tools like what we have in the Green Park to manipulate, to understand, and to test every kind of technology. And if you have any questions about the experience of our invited talker today, please go ahead and ask. If you don't want to ask directly, you can write in the chat and we will follow your questions. So the floor is to the attendees. Please go ahead. Is there any questions in the audience? Please ask. Of course, I'm also in the audience, and I wanted to ask the speaker, you don't give any detail about bifacial module. Have you studied some bifacial? Or in other words, do we have in Horizon tools to do the same for bifacial module, where the light can be absorbed from both sides?
Yes, Professor Ahmed. In the Green Energy Park test facility, there is also bifacial modules deployed with different orientation. So if we want, for example, to investigate the PV or the degradation of the bifacial, we can use the same tools: visual, electroluminescence, IR, and IV measurement. So unfortunately, in my studies, I have not conducted any studies on this kind of technology.
Okay, it's anyway, it's a lot have been done.
There is colleagues that have conducted studies in this technology in the Green Energy Park. Yeah.
Okay, very good. Of course, in this study, if you complete your study with soiling, because soiling also is a problem for the performance, for long-term performance. And also it's important to add this. But we had a soiling conference last time, so the audience. Yes, the student and by Greg Smith and people, they can go. By the way, everyone, he can visit our webpage, and all video regarding our conference are there, and you can, of course, ask again and so on. So thank you very much. So if there is any other questions, please go ahead before we close our day. So now question in the chat, now questions in the audience. So I want to thank you very much, Dr. Abdellatif Bouaichi. I believe that in Rabat are very lucky to have you. PV technology, and Morocco now is a country where they have to go to energy transition and to implement by 2030 and by 2050 a lot of mixed green energetic system, and therefore it's very important. So thank you very much. Thank you for all of you who attend this conference. Next week, the next Friday, I will be the guest for this floor and to give a talk about the inkjet printing technology, which research I have done while I have worked as a research director here in Germany. So I will talk about this method. It's very important, inkjet printing for the future, especially that Morocco will go to the digitalization and industry 4.0. So you are welcome next week on Friday at 6:30 to hear my talk. And thank you very much. And we will close the talk, thanking again the speaker. I hope we will meet him again here in this floor. Thank you very much.
Thank you very much, teacher. Thank you very much for all of you.